I think that you'll be glad you're here because while you can certainly read all this yourself, sometimes it's nice to have someone explain it either before you read it or, that kind of thing. Now, there are some reactions that can't be classified according to these types, but a lot of reactions, especially in our class, can. So synthesis, which is also called combination, is where two smaller things combine to give something larger, or three smaller things combine to give something larger. So I typically write it like this: A plus B react to form C. And it could be something like magnesium combines with oxygen to form a solid, magnesium oxide. And Rhiannon gave you data for a lab that looked like that. Here I have an equation that's unbalanced, but I have the right reactants and products. I've written the formulas correctly. And so now I'm going to add some coefficients. One magnesium on the right, one on the left, one oxygen on the right, two on the left. Oh, I better fix that. To fix it, I can't just put a 2 down here because that wouldn't be the right formula for magnesium oxide. What I need to do is, once I have my formulas written correctly, add coefficients. So I put a 2 here, that fixes my oxygens. I put a 2 there. Now I have a balanced equation. That is one example of a synthesis reaction. The opposite of synthesis would be decomposition. For a decomposition reaction, we have something larger that breaks down to form things that are smaller. A lot of times that takes heat. And so we put a triangle over the arrow to indicate that we've added heat. Sometimes the heat at room temperature is sufficient. So here I have carbonic acid. And at room temperature, it decomposes to form carbon dioxide and water. When carbonic acid is a product, on the product side of the arrow, it automatically decomposes to form these things. There are 3 gas-forming products. Carbonic acid is one, sulfurous acid is the second, and ammonium hydroxide is the third. When these are on the product side of the arrow, we keep going and we say even at room temperature, they're going to react to form gases, decompose to form gases and water. And this has been addressed. It's in your textbook, but it's also in one of the videos where we look at double displacement reactions, going from molecular to total ionic to net ionic reactions. Okay, so decomposition is just something larger, breaking down to form smaller, one thing breaking down to form 2 or 3 things. A third reaction type is combustion. For combustion, you'll be told what the fuel is, and then you need to be able to balance that. So for the first 2 types, you're going to be told what the reactants and products are. Typically. For combustion, you'll be just told what the fuel is. So it's fuel, and then you have to know to add oxygen gas, and what the products of complete combustion are: carbon dioxide gas and water as a vapor. Why? Because combustions are exothermic. They generate a lot of heat, and so water's in the gas phase initially. Sometimes we put a triangle over that arrow to indicate we've done something to start the combustion. We maybe struck a striker or we lit a match, but then once the combustion starts, it proceeds and it's exothermic. A fourth and a fifth type are single and double displacement.
So I have a question.
Yeah.
So would H2O be a gas or a liquid?
Here it's a gas, and here it's a liquid. Okay. It's a liquid for the decomposition of carbonic acid because that happens at room temperature. Okay. But for combustions, it's a gas. Okay. It might cool down and become a liquid later, but when we write the combustion reaction, we write gas.
Okay, thank you.
Yeah. So single and double displacement reactions, these occur in water. And because they occur in water, we can use our table of solubilities or our electrolyte table, same table, to say if things stay together as a molecule or stay together because they're an insoluble solid, or if they break apart into ions like soluble salts do, or like strong acids, they're pulled apart into ions. So we use a solubility table to write total and net ionic equations for those two kinds of reactions. For single displacement, we can predict the product. So we recognize it's single displacement because we have element plus compound. And then we use a table to decide, is this reaction going to go? I talked about this yesterday in Zoom, and there's a video up. And so you need to become familiar with that table. The table is only used for single displacement reactions. If the reaction does go, in our class, the metal becomes a cation, and the cation becomes a metal. So for a single displacement reaction, there's a table we use to predict will the products form. And there's a separate table of electrolytes or solubility table that we use to decide what is the net ionic reaction. For double displacement, we have two compounds and they can change partners. So this cation might go with that anion, or this cation might go with that anion. And then for our products, if it's a liquid, if we formed liquid water, we say that's a neutralization reaction. Or if it's a solid, we say it's a precipitation reaction. So we predict products, and then we use a table of solubilities to see if something actually happened. So that is one way to classify reactions. And this was sort of a review to sort out like how we handle what the special things are for each. Which ones you have to know the reactants and you have to be told the products, or which ones you can predict the products. And then for number 4, you have to decide if a reaction even happens. Okay, another way we can classify reactions is this redox or not? And redox reactions are reduction oxidation. That's what I'm going to talk about. But before I begin, I want to tell you that for these two, synthesis and decomposition, sometimes. It depends on the specific reactants and products, but by the end of today, we'll be able to decide if this time, in this instance, it was redox or not. For decomposition, it is always redox. Oh, sorry. So for synthesis and decomposition, they are sometimes redox and sometimes not. Combustion is always. Single displacement is always. And double displacement is never. So right now, I've basically just talked through, here's the 5 reaction types. There's a different way to classify. And now we're going to talk about what they are, what redox is. And then this last paragraph is, of the 5 types, sometimes they are always, never redox. Okay, so now I want to talk about this idea of what redox is. Redox reactions are electron transfer reactions. A good example might be something like iron, the metal, can become oxidized by air, the oxygen in air, to form rust. So I'm balancing this, and I'm doing it by inspection, which means I'm just looking at things and deciding what the coefficient should be. For redox reactions, there is a more involved way of balancing them that you'll learn when you get to Chem 1B. But for now, we're just doing it by inspection, which means by looking at it. So I'm going to start with the oxygens. I have 2 on the left. O2 comes in pairs, and 3 on the right. So I'm going to shoot for 6. I need 3 of these and 2 of those to have 6 oxygens on both sides. And then I have 4 irons on the right, so I need 4 irons on the left. So here I've written iron as a solid. Another way that I could have said that is iron with no charge. Could iron have charges? Sure. Iron could be +2 or +3. These are the three possibilities for iron. If iron has a net charge of 0, if iron is a solid and an element and a metal, why is that? The answer is because the number of protons equals the number of electrons. So here we have iron, which I think is element 26. Yes. It has 26 protons for a +26 nuclear charge. It has some neutrons. That depends on the isotope, but neutrons are neutral. It has 26 electrons for a -26 charge outside the nucleus. Overall, it's neutral, and that's what that 0 means. When we don't have a 0, it's implied. Okay, so iron here on the left has 26 electrons, but on the right, if we named that compound, we would call it iron 3 oxide. Why iron 3? Because it's lost 3 electrons. So when iron lost 3 electrons to become iron 3, it was oxidized.
So is that the same on our lab then when it says like magnesium metal? That's going to be magnesium with no charge?
Yes, exactly.
Okay.
Yeah, so the word elemental or metal, and then if it's a metal, if it's solid and just the element, it's 0. So iron here went from iron, the element, to iron 3. So it must have lost 3 electrons. And you know that a balanced chemical equation has mass balance and charge balance. So that's what I'm doing here is I have a half reaction that shows how iron is being oxidized. It's an oxidation half reaction. An oxidation half reaction. Anytime that electrons are lost, something else has to gain those electrons. And in this case, it was the oxygen that gained the electrons. So oxygen went from being neutral to becoming oxide. Each atom gained 2 electrons. Because there's 2 atoms, it must have gained 4 electrons. So here we have an reduction half reaction. Oxygen went from having a charge of 0 to having a charge of -2. It went down in number according to the number line, and so that's a reduction. Gain electrons, your number goes down, you're reduced. And then in a different class, I mean, it's not bad for us to see this now. We would look at this and say, well, however many electrons were gained had to come from somewhere. And right now I have 3 electrons lost and 4 electrons gained. That doesn't add up. So I have to multiply by some multiplier. And the multiplier would be here, I'll multiply by 3. And here, I'll multiply by 4. Oops. Not sure my computer's doing here. So what I've done is I've multiplied the oxidation half reaction by 4 and the reduction half reaction by 3. Why did I do that? So that the number of electrons lost equals the number of electrons found. And when I do that, I can combine what's left over. So I'm adding these two half reactions together to get an overall reaction. And in the overall reaction, there are no electrons. Because when electrons are lost, oxidation, and found, reduction, we always have to have all the electrons transferred. Redox reactions are electron transfer reactions. We never have electrons left over. And then I noticed that this could be written this way, which is how we see it up here. So, redox reactions are electron transfer reactions. The electrons are always come from here and go to there, and we never lose an electron. We never have random electrons floating around. There is some vocabulary we use with this, so I want to talk about that now. So before I combine these two half reactions, let's see, I talked about some vocabulary, and I mentioned a number line. So here's a number line. So an oxidation, the charge on iron went from 0 to +3. And when the charge goes up, when the oxidation number goes up, we say oxidation has occurred. For oxygen, the number went from 0, oxygen is an element, to -2. And that's reduction. You do something negative, you become more positive. That's oxidation. You gain an electron, your number goes down. That's reduction. It sometimes bothers students to think reduction is gain. There's two mnemonic devices that we use, and one is Leo goes grr. And Leo stands for lose electrons, oxidized. Gain electrons, reduced. Another way you can remember this is oil rig. Oil stands for oxidation is losing. Losing what? Electrons. Reduction is gaining. Gaining what? Electrons. Because redox is all about electron transfer. So whether you memorize Leo goes grr or oil rig, you need to put one of those mnemonic devices in your head, and then we'll look at reactions, and we'll consider the oxidation state of the reactant and then the oxidation state of the product, and decide if something has gained or lost electrons. And then we're going to put some labels on that. Questions? Okay, so I'm going to go ahead and label this up here. So we would say iron has gone from 0, because I have iron as an element, to +3, because that's the charge that it has in that compound, iron 3 oxide. And if the number goes up, lose electrons, oxidized. They went to the right on the number line. That's oxidation. Oxygen went from 0, the element, protons equals electrons, to -2 in oxide, gain electrons, reduced. Okay, and now I'm going to add 2 more vocabulary words, and then we can get started with some oxidation number questions. When iron became iron 3, and iron lost electrons, lose electrons, oxidized. It went from 0 to +3 by getting rid of something negative. It gave the electrons to something else. Iron gave its electrons to oxygen. And the one who brings about change is called the agent. And so the reducing agent is iron. Iron gave electrons to become iron 3, and by giving electrons, it allowed something else to be reduced. It caused reduction to happen. The thing that is oxidized is always the reducing agent. These always go hand in hand. The thing that was reduced, gain electrons, reduced, took electrons from something and allowed it to be oxidized. The reactant that is reduced, oxygen, is the oxidizing agent. I realize I just flipped my colors. I'm really sorry about that. So the one that is oxidized lost electrons, lose electrons, oxidized. When it gave those electrons to something else, that other thing could be reduced. So it is the reducing agent. The thing that is reduced got reduced by taking electrons, which allowed something else to be oxidized. The thing that is reduced is the oxidizing agent. I want you to notice that the answer to all these questions, what is oxidized, what is the reducing agent, what is reduced, what is the oxidizing agent, they're all reactants. Whenever we're doing this, we're referring to how things were changed. Where did they start? The reactants. Okay, on page 2 of the handout, we're going to talk about how to assign oxidation numbers, because we need to look at oxidation numbers to understand the change. Did the number go up or did the number go down? And so there's 5 rules, and I'm just going to walk through those 5 rules that are on page 2. The first rule is about elements. For elements, the oxidation number is 0. Why? Because the number of protons equals the number of electrons. These are atoms of elements. They're not ions. But we know that elements can exist in 3 ways. We might have a monatomic element. So there's sodium with its 11 protons and 11 electrons, some neutrons. Its oxidation number is 0. There are elements that are diatomic. Each atom being shared has an equal number of protons and electrons. Its oxidation state is neutral. So when we look at the elements that are diatomic, we're still thinking about atom by atom. Both hydrogens here have an oxidation number of 0. Protons equals electrons. And then there are polyatomic elements. There are 3. Each of these 4 phosphorus atoms has an oxidation state of 0, a charge of 0. Protons equals electrons. Rule 2, if something is an ion, the oxidation state is equal to its charge. Sometimes we can see the charge. Here I have a lithium ion, and I can see that it's +1. Its oxidation number, or its oxidation state, same thing, is +1. Sometimes we can't see the charge. Here I have lithium and lithium sulfide. It's an ionic compound, which is made of ions, and so I know the charge is +1 for the lithium atoms here. Each lithium has an oxidation number of +1. The sulfur has an oxidation number of -2. The oxidation state is equal to the charge in an ion. I should add monatomic ion. Let me go ahead and fix that. So sometimes we can see the charge and sometimes we can't see the charge because it's hidden in the compound, but the oxidation state is equal to the charge. Rule 3. We're going to talk about hydrogen. So hydrogen, the element, has an oxidation state of 0. But when hydrogen is in covalent compounds, the oxidation state is +1. So it might be in a covalent compound like water. Each hydrogen in water has an oxidation state of +1. It might be in a covalent compound like ammonia. Each hydrogen in ammonia has an oxidation state of +1. It is possible for hydrogen to be in an ionic compound. It's not going to happen in our class very often, but it does happen in organic chemistry quite a bit. And there the oxidation number is -1. So we could have sodium hydride. Sodium is +1, hydrogen here is -1. Lithium aluminum hydride. Sodium borohydride, you don't need all of these. For hydrogen, when it's with with metals, it behaves as a nonmetal that's gained an electron and is isoelectronic with helium. So there is the possibility that hydrogen has an oxidation state of -1, but not in our class. That's something that you'll see in organic chemistry. I mean, you may see it once in our class. So let's look at this one. Will you stop? Excuse me. So is that ionic or covalent? Hydrogen chloride. That's covalent. Because even though hydrogen is with the group 1 metals, it is not a metal. It's a non-metal. So the oxidation state for hydrogen there is +1. Rule 4 is oxygen. So oxygen in any compound, ionic or covalent, is -2, typically. Sometimes it's -1 and sometimes it's -0.5. So I'm going to show you some exceptions. The oxygen in peroxide there's 2 atoms and it adds up to -2. So each one must be -1. The oxidation state or number for oxygen and peroxide is -1, but it's not stable that way. That's why we use peroxides to clean contact lenses, to bleach hair, to bleach teeth, because it's unstable. It's going to change pretty quickly. There is something called superoxide, which is even less stable, and it's used by firefighters and self-contained breathing apparatus. When you drop water on a superoxide, it generates oxygen gas. And so if you were going into a burning building with a lot of smoke, this would be something that wouldn't be nearly as heavy to have on your back as a tank of oxygen. We would never use this for scuba diving because it's water that causes superoxide to become oxygen gas. If you had a crack in your tank, you'd blow up, so that'd be bad. But superoxide is a real thing. Since there's 2 atoms of oxygen and it has to add up to an overall charge of -1, each oxidation number is -0.5. So peroxide and superoxide, those are real things. Are you going to run into superoxide in your life? Probably not unless you're a firefighter. Why do I mention it? Because I want you to see that the idea of electron transfer isn't really actual electrons. You can never have half an electron, but you can have the idea of half an electron. So there are going to be fractional oxidation numbers sometimes. The only fractions you will see are a half, like maybe 2.5, and there will be a time when you see a third. It is possible to have -1/3. Okay, so oxygen typically is either 0, because it's an element, or it's -2, but there are some other possibilities. Here I have oxygen. What would the oxidation state be for that, for each of those 3 atoms? The answer is 0 because ozone is a polyatomic element. And for elements, the oxidation number is 0. Okay, and then the last one is rule 5, which is super handy. And the idea goes like this. If we have a covalent compound or a covalent ion, the oxidation states all have to add up to 0 if it's a compound or the charge if it's an ion. And so this idea of an oxidation number is a pretend number. Sometimes it's a real charge, but sometimes it's just the idea of a charge. If we had a compound like phosphorus trichloride, which is covalent because phosphorus is a nonmetal, and we wanted to state oxidation numbers, the one on the right, we're going to pretend it's an ion. What charge would chloride have as an ion? So here I have 1 phosphorus and 3 chlorides, and they have to add it to 0 because right now we're talking about a compound, and a compound has a net charge of 0. So I'm going to substitute -1, which is the charge chloride would have as an ion. It's not an ion in this compound, we're pretending. and say phosphorus minus 3 equals 0, what's the oxidation state for phosphorus? Plus 3. Now, does phosphorus have a charge of plus 3? No. It's just in this setting with chlorine, because chlorine is more electronegative. Chlorine hogs the shared electrons, and phosphorus, it's like it has a plus 3 charge, even though it doesn't actually have a plus 3 charge. So for rule 5, we're just playing a game, and the one on the left is pretending to be the cation, and the one on the right would be like the monatomic anion. And then we do some math and see where the numbers fall out. So that works for anything that's covalent, which could be a molecule, it adds up to 0, or an ion, it adds up to the charge. So now I want to look at cyanide ion. So cyanide is a polyatomic ion that has a charge of -1. So the oxidation state for carbon plus the oxidation state for nitrogen has to add up to -1, the overall charge. Because nitrogen is on the right, I'm going to pretend it's nitride. What charge would nitrogen as a monatomic ion have? -3. Because it's in group 5, it would be -3. So carbon -3 has to add up to the overall charge, which is -1. Add 3 to both sides, and in this setting, carbon has an oxidation state of +2. So for things that are covalent, we pretend the one on the right has the charge it would have as an ion, and we pretend the one on the left is the cation, and there's a lot of charge choices that are possible. Questions? Okay, so what charge choices are possible? Let me talk about that for a second. I'm just looking at rule 5 right now and nonmetals and saying, what are the possibilities? If a nonmetal is in group 4, like carbon, the possibilities range from the group number to 8 minus that. For things in group 5, like nitrogen, it could be the charge it would have as an ion to the group number. Group 6, not oxygen, but below oxygen is sulfur. Sulfide would be -2, and the group number is +6. Those are the range of possibilities for anything in group 6, any nonmetal in group 6. Group 7, like chloride, could be -1, up to +7, the group number. Things in group 8, they aren't going to do this. They're too stable. So oxidation state, which is the same thing as oxidation number, is the idea of charge, even if actual charge isn't possible. For my first example, I took iron and oxygen to make iron 3 oxide. So there was actual electrons being transferred. But for my next example, we're going to look at combusting methane. So methane has a formula that you've memorized. And combustions, you know how to write those reactions: add oxygen, predict the products. So go ahead and balance the combustion of methane. I start with the fuel, 1 carbon here, 1 carbon there, 4 hydrogens. I need to put a 2 here. And then I see that there's 2 oxygens plus 2 oxygens is 4 oxygens. I need a 2 here. So the way I've written it, my coefficients are 1, 2, 1, 2. Now let's go ahead and assign oxidation states for each atom. The easiest one is oxygen. It's an element, so the oxidation state is 0. And then let's do water next. Hydrogen in a compound is +1. Oxygen in a compound is -2. For methane, I have carbon plus 4 hydrogens adds to the overall charge is 0 because it's a molecule. And hydrogen in compounds, covalent compounds, is +1. So the oxidation state for carbon and methane is -4. Now let's do carbon dioxide. Carbon plus 2 oxygens equals 0. But oxygen in compounds, ionic or covalent, is -2. So carbon plus 2 negative 2s equals 0. So here, carbon is +4. So carbon and methane is fully reduced. Carbon and carbon dioxide is fully oxidized. Methane is a much worse greenhouse gas because it's not going to stay -4. It's going to become oxidized to +4, and damage is done. Heat is added when that happens. Okay, so now we're looking at each kind of atom in each compound. And notice that here, for example, I'm just saying +1 for hydrogen. And in my head, I know there's 4 hydrogens, but I'm looking at each oxidation number for each atom. So we want to figure out what's changed on the left and the right, which atom was oxidized and which atom was reduced. And all the answers are going to be reactants. So go ahead and label what is oxidized, what is reduced, what is the oxidizing agent, what is the reducing agent. So the answers to all of our questions have to be reactants. In order to make it clear to the person grading that you're talking about reactants, I can't just say carbon was oxidized. I need to tell you which carbon. It was the carbon in methane. And then oxygen was reduced from oxygen, the element, to either oxygen and carbon dioxide or water, but it was reduced the same way. So when I write oxygen and oxygen here, I'm simply saying oxygen is the atom that gained electrons, and it was in a reactant species. Questions? Okay, so on page 2, we talk about what the rules are. At the top of page 3, it says what the possibilities are for the different group numbers. And then it says determine the oxidation number for these things. So for number 1 on page 3, A through H, we're figuring out for chlorine what the oxidation state is. Why? So when we see an equation, we can decide if it's been oxidized or reduced. Okay, so when I do it, if I have something like B, I can pull off the cations to figure out what the anion is. And then here, I'm just dealing with the anion. 1 chlorine, 2 oxygens, 1 chlorine, 2 oxygens, add up to the new overall charge that I just exposed. Sometimes it's easier to do that way, and I'll give you an example in a minute. Okay, so for the first one, chlorine minus 6 equals -1, it must be +5. Chlorine minus 4 equals -1, add 4 to both sides. Chlorine is +3. Chlorine minus 2 equals -1, add 2 to both sides. +1. Okay, so it's kind of messy there. I'll go ahead and highlight my answers, but if you have questions, please let me know. Okay, on page 3, number 2, it says find the oxidation number for each of the elements on the left. So maybe if you're done here, you want to get started on that, that'd be fine. Are there any questions out there? Okay, so I'm going to do an example at the top that might be helpful. So this business I did with B, where I kind of separate the cation and the anion, they can help us. Let's say you had something like this, and you were asked what the oxidation state of iron is. Can you name that? Yeah, it's iron 3 nitrate. And if it's iron 3, the oxidation state is +3. Because in this case, for an ion, the oxidation state is equal to the charge. If we were asked for the oxidation state for nitrogen in that compound, I wouldn't want to take the whole thing and break it apart. 1 iron plus 3 nitrogens plus 9 oxygens equals 0. Holy moly, that's a mess. But if I pull the ions apart and just look at nitrate individually, I can say, well, nitrate is NO3 minus 1. This is covalent because those are both nonmetals. The one on the right gets a charge, so oxide would be minus 2. And the one on the left we're going to figure out. Nitrogen plus 3 oxides adds up to the overall charge. Oh, in this situation, nitrogen is plus 5. So there's times when it is easier to just dismantle a thing and look at a smaller problem to find the answer. And that's what I was doing in B, is I was pulling sodium chlorite apart so I could just look at the chlorine and chlorite. I don't know if that helps. Okay, so we're running out of time. I'm going to go ahead and do number 2 real quick. Let's look at the chromium and dichromate. We're looking at the element on the left. There's 2 chromiums. Oops. And 7 oxygens. Oxygen is -2 in compounds. It adds up to -2 overall. 2 chromiums minus 14 equals -2. Add 14 to both sides. 2 chromiums is 12. So each chromium atom must have an oxidation state of +6.